Hey there everybody, Mr. D here, and in this video we are going to wrap up our pre-calc/alg 2 recap with discussing piecewise functions and what that might indicate for domain and range. So let's remind ourselves, what the heck is a piecewise function? Piecewise function, I like to call these Frankenstein functions, is when you have different components of different functions all smushed together on one graph. One thing to keep in mind though with a piecewise function is it does have to maintain its function status, meaning it passes the vertical line test, which is why you will never see two filled in dots directly above one another. So if at any point there is a jump where my graph transports from one area to the next, one of those dots will have to be, at least one of those dots will have to be open. The other one might not be filled. All right, so let's take a look at this particular piecewise function. We've got three different components here. I've got what appears to be a straight line. Well, that looks like a linear function with a slope of up 1 over 1. If I continued that pattern, the y-intercept would have been 5. So I've got y equals x plus 5 is represented here. And then we transition into this little parabolic section. Well, that looks like a parabola that got shifted down 1. There's no stretch factor because it goes up 1 and over 1 in each direction. So I've got y equals x squared minus 1. And then I've got this, looks like a sideways parabola, just the top half though, so that is a square root function. We got shifted to the right 1 and up 2, so that would be the square root of x minus 1 with a plus 2 on the outside. So those are the three components for this piecewise function. Now if I were to list the domain, as I go left to right, my x value is defined here, defined here, defined here, defined here. Right here is where it gets weird. If I plug in 1 for x, do I have a y value? Well, yeah, it's right here. It's 0. If I had 0.99, that would be right over here. If I had 1.001, that would be right over here. But specifically at 1, my y value is in fact 0. So this thing is always defined. Therefore, the domain is negative to positive infinity. Now the range, we have to be a little careful for. It might not happen in this one, but it could happen down the road. The range is as I go bottom to top, low to high. Well, this function goes down forever, so I know there will be a negative infinity. It goes up forever, so there will be a positive infinity. But the weird stuff in between. Now, some of us might be tempted to say, all right, negative infinity to 0, and then there's this gap, and then 2 to 1. But what we have to keep in mind is that as I'm going from bottom to top here, right here, even though the function's not defined over here for a y value, we do have y values defined over here. So we're still good. There's still a function definition, again over here. And then as we get higher, we still have function definitions. Heck, we have 1, 2, 3 different function definitions there at that given y value. So this actually does maintain all real numbers as its range. Now some people might get caught off guard by that. Now let's play a little hypothetical, play a little what if. Let's say what if this little square root function was just a little bit higher up. Well then yes, there's a clear gap right here. So you'd have negative infinity to 3 and then from 5 to positive infinity. So here there's a clear gap. But the way it stands, there was no break in y values. All right. Now let's talk about how to evaluate piecewise functions. Here we have an example of a piecewise function. Hey, that looks familiar, doesn't it? Looks like the one we just did. And there's two ways to tackle this. First one is just looking at the graph, right? So if I wanted f of negative 4, go to negative 4 for x, I get 1. F of negative 2, go to negative 2 for x, I get 3. Go to 1/2, go to 1/2 for x, I'm going to get something. Go to 5 for x, I'm going to get 4. So if you have a graph, you can just look at the graph, right? Plug in the x value and just look. But let's say, what if we don't? So we're going to play dumb here, and that graph does not exist. Instead, what I'm going to do is say, okay, I know that f of negative 4 has an x value of negative 4, and this first function rule is for all x values less than negative 4. Or sorry, negative 2. Negative 4 falls into that category. Negative 4 is, in fact, less than negative 2. Then I've got this next function evaluation at negative 2. Well, that falls into this category here. This is for all x values that are between negative 2 inclusive and 1 inclusive. Now this next one is 1/2. 1/2 also falls into that category of being between negative 2 and positive 1. Lastly, I have 5. Well, 5 falls into that category of being bigger than 1. So we're looking at those x value restrictions as to how to know which of the 3 functions to plug into. And the way we do that is we look at our domain restrictions here. All right, so let's evaluate. If I plugged in negative 4 for x, negative 4 plus 5 is 1. If I plugged in negative 2, we'd have negative 2 squared minus 1. Well, negative 2 squared is 4 minus 1 is 3. If I plugged in 1/2, that would be 1/2 squared minus 1. 1/2 squared is 1/4 minus 1 is a negative 3/4. If I plugged in 5, well, that would be the square root of 5 minus 1 plus 2. Well, 5 minus 1 is 4, square root of 4 is 2, 2 plus 2 is 4. Now let's confirm and see if that matches what we thought earlier. F of negative 4 is 1? Yup. F of negative 2 is 3? Yup. F of 1/2, I didn't know what that was, but now I do. It's negative 3/4. F of 5 is 4. So algebraically, we're getting the exact same thing that we got by looking at the graph. So now let's graph a parent function. There's a few ways to do this. One, you could make a table. I'm not a huge fan of that. We'll showcase that in class, but for the sake of this video, I'm going to show you kind of the parent function method for it. And then, actually, I guess we do it with tables here. So we will discuss it. I'm not too thrilled with that method, just as a FYI. All right, so I'm going to do this all in one go instead of breaking it down section by section. All right, this first function here, negative 2x minus 3. That, as a function, is going to be a slope of negative 2 and a y-intercept of negative 3. So that's going to be a line, okay? And that graph only exists when my x value is less than negative 1. Then my second function, this negative x squared plus 2. Well, that's going to be a parabola that opens down, and it went up 2 units. So it's going to look something like that. And then lastly, I have y equals negative 2. So that's just a horizontal line. That's going to have a slope of 0. All right. So I know generally what the shape of these 3 components is going to be. Now what I also know is, where do I switch from one to the next? Well, I switch at negative 1. Negative 1 is where I go from this blue function to this green function. So what I'm going to do is draw in a little dotted line. It's almost going to be like an asymptote, but it's not an asymptote, just for reference here. And then I switch again from at 2 from one function to the other. So when x is 2, I switch from the green to the red. So I'm going to do the same thing when x is 2. Just going to plug in a different dotted line there. So everything over to the left of -1, all of this follows that blue function pattern. Everything between them follows that green functions pattern. And everything beyond 2 follows that red functions pattern. Well, that blue function, we said that that was a slope of -2, y-intercept of -3. If I were to start graphing that, y-intercept is -3, slope is -2, so I get a whole bunch of dots going. I'm running out of graph in the bottom right, so I'm going to go backwards. You can see I clearly have a line shape, but my function is only defined on this side of that little boundary. So I'm not going to connect all of the dots, I'm only going to connect the ones that have an x value less than or equal to -1. Now, since this has an or equal to, I can include a filled in circle. Now, for this middle function, we had -x squared plus 2. So that was a parabola that opens downward, shifted up 2. So I have my little dots here, go down 1 over 1, then down 3 over 1, then down 5. I ran out of room. I've got some symmetry going on here. You can clearly see I've got a parabola. But I don't need all of these points. I only need the ones in between -1 and 2. So I'm only going to select those to graph. Now, neither -1 or 2 are included. That's strictly less than symbol, which means I have to have an empty circle. So filled in inequality symbol, filled in dot, if it's included. All right, last one. We have -2. Well, that's just a horizontal line that extends forever. Now, this one is included, and it's directly on top of an empty circle. So that filled in circle actually fills in the empty circle. So this, my friends, is what our graph would look like. Now, we can do the same thing, graphing with tables. Spoiler alert, that's what the graph is going to look like. Let's act surprised when we get there. For the record, I am not a huge fan of doing it this method. I think it takes too long. I think it potentially confuses people, but if you like it, go for it. All right. I've got 3 different functions. I've got a parabola shifted to the left 2 units. I've got a cubic function that didn't get shifted anywhere. And I've got an absolute value function that's upside down, went right 3, up 1. So I'm going to have this first table is going to be my parabola. This second table is going to be my cubic. And this third table will be my absolute value. I need to pay attention to what the x values I'm concerned with here. I only care about x values that are less than -1. So I'm going to fill in my table with x values that are less than -1. So -1, -2, -3, -4. Now, I realize that -1 is not strictly less than -1, but I still need to know where that graph is headed, so I'm going to make a little note that this point right here is not actually included. So now we'll plug in all these values. I'm plugging into this blue function here. -1 plus 2 is 1. Square it, I get 1. -2 plus 2 is 4. Square it, I get 16. -3 plus... Ooh, I screwed up. Pardon me. -2 plus 2 is 0 squared is 0. -3 plus 2 is -1 squared is 1. -4 plus 2 is -2 squared is 4. There we go. Then we go on to the green function. That green function is only defined from -1 to 1. So in my table, I'm going to write out -1, 0, and +1. -1 is included, but +1 is not, so I just need to make a little note of that. +1, you're going to get an empty circle, so I just don't want to forget that. -1 cubed is -1. 0 cubed is 0. 1 cubed is 1. Lovely. And then lastly, x is greater than or equal to 2. So I'll have 2, 3, 4, 5. I'm plugging these values into this absolute value function. So 2 minus 3 is negative 1. Absolute value of that is 1. But there's a negative sign in front, so it's back to negative 1. Negative 1 plus 1 is 0. Plug in 3. 3 minus 3 is 0. Absolute value of 0 is 0. Negative 0 is 0. Plus 1 is 1. Plug in 4. 4 minus 3 is 1. There's a negative out front, so negative 1 plus 1, we get 0. Plug in 5. 5 minus 3 is 2. Absolute value of that is still 2. There's a negative out front, so negative 2 plus 1 is negative 1. So now we will graph all of this. Oh boy. Negative 1 comma 1, empty circle. Negative 2 comma 0. Negative 3 comma 1. Negative 4 comma 4. We've got a little parabolic shape there, which we should have been able to look at that and we would know. Then in the middle, x cubed, negative 1, 0, 0, and 1 comma 1 with an empty circle. That's a cubic function, so it's going to have a little curvature to it. And then lastly, our upside down absolute value function. We have 2 comma 0, 3 comma 1, 4 comma 0, 5 comma negative 1. That's what that function would look like, and holy smokes, wouldn't you know it, that's what we had there. So again, this is another way of doing it. I personally prefer just kind of graphing what the parent functions are, so I'll have extra points there that I can always erase. If you don't like that method, you can make tables, but in my humble opinion, I feel like this method just takes forever, especially when you have all these little tiny computations that you're doing. But you do you. Find out whichever way works for you. That's it for this video. You know the drill. If you have any questions, please feel free to ask. And as always, folks, good luck, have fun, be safe, roll tide.